to take the exam, we had to measure or calculate or predict the pH of some solutions. And these solutions, I don't know if you recognized them, but they were all what type of acid? Strong. So if I said it was 0.2 molar acid, right, 0.2 molar HCl or whatever, you always knew the concentration of H plus was 0.2 molar because it was a strong acid. The technical jargon is that it's 100% dissociated. Fine. However, in nature and in real life, you're not going to come across the strong acids all that often. It's going to be, because there's only 6 of them. And there's millions and millions of acids, but there's only 6 strong ones. So the majority of everything in life is going to be like vitamins. It's going to be like those pollutants. It's stuff that's a weak acid. And to monitor the pH of a weak system, it's going to involve some math. We can't just say, oh, it's 0.2 molar like we could with a strong acid. So we'll have to do some calculations. So how do we recognize the solution with a strong acid? How do we do that again, Monica? Yeah, HCl, HNO3. It's one of those 6, right? So know those 6 strong acids. What were they again? HCl, HI, and HB. Okay, there's the half of them. There's the halogens. Then you had H2SO4, HClO4, and HNO3. Right? Okay. How do you know if a solution is a weak acid? It's not one of those. Right? Exactly. It's not one of those. And then if I ask you for the pH of a weak acid solution, oh, it's going to be some work. Okay, that's where the job security is going to come in. So a weak acid, it's dissociation reaction or acid ionization reaction. Okay. In general, we're going to call the acid HA. Right, so that's the conjugate acid. It's H is the acidic hydrogen. Remember, HA could dissociate or fall apart to what and what? H plus and A minus. Now, I don't really like how I have that arrow drawn because that arrow makes it look like it's 100% dissociated. That makes it look like it's a strong acid. So instead, it should be, if you got rid of that guy, it should be a little tiny arrow going that way and a huge one going back because it hardly breaks up, right? But, you know, we're kind of lazy. In fact, we're even lazy. We should have what subscripts on here? Not gas, but we should have AQ. All the time we should have AQ. 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 What does AQ stand for? Aqueous, dissolved in water. So, but, you know, we're lazy. We're going to be lazy with, at least I am. I'm going to be lazy with this double arrow thing. I'm going to be lazy with the AQ. In fact, I'm probably never going to do it again. Okay, just realize that's what's going on, though. How would you write the equilibrium constant expression for this? Lauren, how would you write it? It'd be what over what? Products over reactants. So you'd write H plus in brackets, right? And A minus over HA. Right? Because HA is not a liquid, it's not a solid, so you got to have it in there. When you have a subscript on a equilibrium constant like you do here, it means you have to write the reaction a certain way. Because you see a table coming up in table 16.1. And they have all these numbers for the Ka. Those numbers are going to be totally wrong if you don't write the reaction correctly. How do you write the reaction? You have to write it in this format. Right? The acid going to its ions and breaking up. Product, reactants go into products. So the reactant is the acid. If you don't write it that way, nothing's going to work out. So make sure you write the reaction in that format. The acid going to its H plus its conjugate base would be the technical word. Okay, if we play around with this table a little bit, what do you think, Brandy? Larger or smaller or no effect? Acid ionization constants mean a stronger acid. What do you think? Everybody agree? Now remember, acid ionization constants or equilibrium constants, they're all what over what? Products over reactants. Now our products in this are H plus and A minus. If it's the stronger acid should have more what? The stronger the acid, you should have more what ions floating around? What ion were we thinking of? That's our acid. It's H plus, right? So the more H pluses you have available, the stronger the acid. Well, K's are products over reactants, and look what's up on top. H plus is the larger. Yeah. The larger the Ka, the stronger the acid, because of a blank degree of dissociation. Albert, what would you guess there? Lower?
I'm thinking of the KC, like it's 1.10 to the negative 5.
Yeah.
Compared to 5.9, 10 to the negative 10. Strong acid would be negative 5.
Exactly. That's right. You're thinking that's right.
That's why I picked the
Yeah. The 10 to the negative 10 is definitely smaller than 10 to the negative 5, so the 10 to the negative 5 would be a stronger acid. Okay.
That's not what we're talking
No.
about.
It's yeah. They're not talking about exponents or anything. They're just talking about dissociation. They're using the terminology. Things breaking apart. Things decomposing. The stronger acids are going to dissociate more. They're going to break up more. Break up into that H plus and A minus more. Okay. Table 16.1 lists the acid ionization constants for some weak acids. Which acid listed is the strongest? Okay, now we're getting into what Albert was looking at. Mari, which one would you say is the strongest acid in there? They're all supposed to be weak, but it's the strongest of the weak. We're looking for the biggest Ka in here, right? Which one would it be? H2SO3. Where do you see? Okay, do you see one bigger than 1.3 times 10 to the negative 2? Is there a bigger one than that one? H2C2. How about how about that one? Is there a bigger one than 5.6 times 10 to the negative 2? Right? I think that's the biggest one. Now hydrogen sulfate, looks like this is 0.011. That's what that one is. This one is 0.056. All right, so it's bigger. She's right. Whoever picked out oxalic acid. All right, strongest would be that one. The weakest one, the smallest one. Yeah, I'd say it's that 10 to the negative 13 one, right? You'd be the weakest. Write the dissociation reaction and Ka expression for the weakest acid in the table. Write the dissociation reaction and the Ka expression for the weakest acid. Now we said the weakest acid was HS minus. So Victoria, how would you write the dissociation reaction, the Ka reaction for HS minus? What would you write?
So it's going to be oxalic acid over the hydrogen.
Well, no, not oxalic. They want the Ka expression for the weakest acid, and we said that was HS minus. So you have to put HS minus here.
And then it's going to be
The H,
the concentration.
yeah, H plus and
H plus and S.
then S with -2. Yeah, because you got to take away an H plus. So you got it already is a negative, so you take away another plus, and you have -2. Did you notice a trick to doing this is HS minus overall charge -1. Well, the charges have to be balanced on both sides. So over here, you have a +1 and a -2. Adds up to be a -1. So that's another trick to doing this. Oh, and they want the Ka expression. Fine. Products over reactants. Okay. Calculating equilibrium concentrations of a weak acid solution when given its Ka and initial concentration. Okay, so we've got formic acid. It's used to make ethyl formate, an artificial rum sweetener. What's the pH? A 0.01 molar solution of formic acid. Let's start with the question here. How would you get your answer? Solve for the H plus, because what's the equation for pH? Did you hear Maria? We need to know the concentration of H plus, right? We need to know it. Then we'll take the negative log of it, and we'll have our answer. And that's the concentration of H plus at equilibrium. They're not asking for the concentration of everything there. They just want H plus. But still, it's a what problem? Ice. It's got to be. That's the only way we have to get concentrations at equilibrium. It's ice. So we have to do ice. But we're going to do ice of what reaction? What reaction? Yeah, that HCHO2 going to H plus and its conjugate base. The Ka reaction. And there's a lot of different ways you can describe it. You can say the Ka reaction. That's how I like to say it because that's the equilibrium constant that corresponds to it. The Ka reaction, the dissociation reaction, the acid ionization reaction. There's a lot of different ways to say the same thing. But HCHO2 going to, what would you say? Caroline, what would you say? It's the rest of it. Going to what and what? Thank you. Phone a friend. Okay. We're good so far. Okay, we need, Alyssa, we need to fill out that initial row. Point 1, you're going to put it where? Yes. You agree? Okay. Zeros or dashes, whatever you like to write. Okay. The change row. Monica, how did we do that again? What are you going to put in there?
You do
Minus x. Plus x. Plus x. Okay. And Maria, now what do you do? 0.1 minus x and x and x. Okay. So at equilibrium, here's all of our answers. Right? Those are all of our equilibrium concentrations. So it looks like we just need to take the negative log of what and we'll have our answer. Do you see it? Take the negative log of x. That's all we're going to be doing. Taking the negative log of x and we'll have our answer. Because that's what the hydrogen ion concentration is. Okay. So let's keep going. Ramiro, now what would you do? That Ka constant, yeah. Ka H plus CHO2. Is it plus or is it times it? I mean, is it, do we multiply these guys or are we adding them? Multiply, keep going. Okay, good. Keep going. Yeah. Okay. So we substitute stuff in here. We'll have 1.7 times 10 to the negative 4 has to equal pretty much just x squared, right, over 0.1 minus x. You agree so far? Okay. Now, wouldn't it be super nice, Lauren, if I could, let's write this in, I don't know, this color. 1.7, the color of blood, because if we screw up, it's going to be bloody. Would it be nice to write that? And if so, why? Why would that be nice? Monica was on to something there. Did you hear what she was mumbling about? She said you don't have to use the quadratic formula. You see it? If we could write this thing in blood, take the 1.7 times 10 to the negative 4, take it times 0.1, then do what? Square root. You'd have your x. There's none of this quadratic formula stuff, right?
Are you sure?
So here's the question. We could do that if x is really what? Eric, what does x have to be for us to do this? X is big. 0.1 minus something big, you're not going to, right? You're not going to get 0.1 again anymore. Okay, less than 0.1. How much less than 0.1? Well, if it was the same, you, because what we're trying to jump from, we're trying to jump from this thing and have that turn into this thing. If it was 0, right? Okay, now if it's 0 though, what would the hydrogen ion concentration be? 0, and then we're screwed. You know that isn't going to work. So 0 is going too far. It's not going to be 0, but it could be really super, super tiny, right? Take 0.1 minus a super, super tiny number on your calculator, and then you'd get, I don't know, 0.09999, right? Does that make sense? Well, 0.099999, you don't write 0.099999. You just write 0.1, don't you? We've been doing this forever. We've been rounding. We said goodbye to sig figs a long time ago, even though we're not supposed to. If x is really, really small, we can write this. Okay, so that's the first thing to realize. And then you really want to, because then you see how to solve it. It's pretty quick. How could x be really, really small? The trick to doing that is looking at the Ka. Look at that Ka. Right? This number right here, that's our Ka. And we've got a bunch of them over here too. There's going to be some cases where you can, all I want us to do is look at this table, look at the Ka number and say, oh, man, it's okay. I can do this. So what Kas would that be? Kas that are huge or Kas that are small? Kas that are small. Why? You're exactly right. And the smaller the better, because all of this is wrong.
Closer to 0.
Ka is really, really small. All right, look over here. Ka is really, really small. You'd have a whole lot of product or a whole little bit of product. Small amount. Small Ka means small amount of product. Well, H plus is a product. But according to our table, H plus is X. So the smaller Ka is, the smaller what will be? X. And the smaller X is, oh man, it's even better. Okay? So the rule pretty much is 10 to the negative 4 or smaller. That's good enough. And you can jump from 0.1 minus x to 0.1. Now, 10 to the minus 4 or smaller, what's the next exponent then? 10 to the negative 5, 10 to the negative 6, 10 to the negative 7. And you get even better and better answers. 10 to the negative 4 is kind of like, well, okay. Well, we'll find out. We'll show you when we solve the question. But the smaller Ka is, the better, the more exact solutions you're going to get.
What times it by 1 and square root?
Take it times 0.1.
Oh,
All right, so let's do that. Make sure we can get our x. Our Ka is 10 to the negative 4, so we're going to just say that 0.1 minus x is 0.1. Take the Ka times, let's see, 1.7 times 10 to the negative 4 times 0.1. And then take the square root. I got about 4.1 times 10 to the negative 3. Yeah. Okay. Make sure you can get that. So is 4.1 times 10 to the negative 3 smaller or a lot smaller than 0.1? Yeah, I mean, it kind of is. I mean, 0.1 is, well, 0.1. 4.1 to 10 to the negative 3 is 0.004. So, I mean, it's smaller, but it's not hugely smaller. But it's a lot smaller. Factor of 100 at least. So it's not bad. Okay. So this is what we're going to use for our x. So that's the game we're going to be playing. As long as we have a Ka that's 10 to the negative 4, negative 5, negative 6, we can make that step. Otherwise, ugly. Let's finish this. So that's my x. So what's my final answer then? Take the negative log of it. Negative log of 4.1 times 10 to the negative 3. About 2.4. Okay? Okay. So Brandy, does this make sense? So Albert, let's ask you. Make sure everyone's on the same page here. It all depends on you. Imagine this. Smith is in a really, really piss-poor mood. For the quiz next time, right? Really, really piss-poor mood. What Ka would he probably give you? 10 to the what? What Ka would he probably give you? I want you guys to work like dogs. Now, 10 to the negative 4 is right on our borderline. We can still drop it. 10 to the negative 3, 10 to the negative 2, 10 to the negative 1. Anything bigger than 10 to the negative 4. And then you're going to have to do a full quadratic, right? So just, we'll see what kind of mood I'm in. Okay, try this one. Set this one up. They want to know what the pH is of 0.38 molar HCN. Okay. Now, check out the Ka. It's nice. 10 to the negative 10. So when you get that far, the math will be a lot easier. But nothing changes. You have to set everything up. You have to set up ice. You have to set up your Ka expression. Nothing changes. They're after pH, so you have to find the hydrogen ion concentration. And make sure you write your acid ionization reaction, the Ka reaction, the right way. Otherwise, that Ka is not valid. You have to start with the reaction. HCN goes to H plus NCN minus. Then you do ice on it. So if you don't start with the right reaction, yuck. Good luck.
Dr. Smith.
Hmm.
Alright, I'm gonna solve it first and then I'll ask you.
What?
Well, on
It's
the
not
other,
going to work.
yeah, that's what I was gonna ask. But like in the other problems, why don't we just like if H was
That's not HCN isn't a strong acid.
true.
You could do that, Monica. You could do negative log of 0.38 and have your answer if HCN was one of those 6. But it's not. But it's not.
That's what it's like if that's fine.
Okay. So this is as far as I got. I don't know if you're... I set up the ice table. All right. Anybody get an X? What'd you get for your X? You didn't take the square root? Not yet? Oh, I just want to write an intermediate step in case someone screws up. 4.9 times 10 to the 10 negative times 0.38. About 1.862 times 10 negative 10. So I have to take the square root. So I took 4.9 times 10 negative 10 times 0.38, and I got 1.862 times 10 negative 10. Okay. Then I need to take the square root of that. Did you get 1.36 times 10 negative 5? Excellent. X. 1.36 times 10 to the negative 5. Everyone got it? All right. I need pH, so I need to do what? Take the negative log of it. Exactly. Because my X is my H plus concentration at equilibrium. So about 4.9. Everyone got it? Okay. Little bit of a twist. Interesting. Well, it's a consequence. Okay. Luck. Coincidence. Find the Ka for a weak acid if the pH is 2.8 and the concentration of HA is 0.52. Okay. It's different. Very different. Victoria, what are you gonna do? A game plan? Yeah, she's getting on to. She said a few things here, right? She's messing with the pH. It's just attend to the something, right? And then she said find the concentration of each. She's on to something here. Why do you need to find the concentration of each? Because I say you start with what they're asking. Find the Ka. Well, that means you just have to write the Ka expression, right? Because what else could you write? Ka is going to be, we should probably write the reaction, otherwise it's kind of hard to write. Let's write the reaction first. What reaction are we going to write, Alyssa? The HA going to H plus plus A minus. So then it's a lot easier to write the Ka expression. Monica, what would you write for the Ka expression?
H plus
Yeah?
A minus
Mm-hmm.
over HA plus.
Or HA. Right? So we just need to find the concentration of each, is what she said. What Victoria said. She's right. You've got to find the concentration of each. So Maria, how are you going to do that? She says start by solving for the concentration of H plus. How? Okay. She's talking about, do you remember this? She says 10 to the negative pH. Remember messing with that? There's our hydrogen ion concentration. Okay. Now, she's kind of jumping ahead for my thinking, but it works. Where I was thinking, when I first read this question, I thought it's the exact opposite of this one. We're always after pH. But, right? But in that question, they gave it to us. So in other words, they gave us X. And then they're going backwards, right? They gave us X, then we just substitute into the ice expression, and we know what everything is. That's what I was thinking. But what Maria was talking about is probably a little more direct, right? Okay. So 10 to the negative 2.8 is 2.8, make it negative 10 to the x, 1.58 times 10 to the negative 3. That's my hydrogen ion concentration. But what are the rest? So we have hydrogen ion done. Great. But HA and A minus? Well, HA is 0.5. Technically, it's 0.52 minus X. And what is A minus? It's the same as the H, yeah. So if you don't see it, I have to fill this ice table out. I don't know if you can see it. You're seeing that H plus is the same as A minus, and HA is 0.52 minus X. You don't know if it's 0.52 or not, because you don't know what Ka is, right? If Ka is 10 to the negative 5, negative 6, negative 7, then it is just 0.52. But really, it's 0.52 minus X. So anyway, I say you fill this thing out. And then it's much more straightforward, right? 0.52, just like always. Negative X. X is 0.52 minus X. X and X. So you see how all of your, here's your answers right here. Then you have to memorize anything. Oh yeah, A minus is X. H plus is X. And HA is 0.52 minus X. So you pretty much just find out what they all are and substitute it in there. And now you know what X is. Right? Substitute them all into here. You'll get your Ka. So for HA, you put in 0.52 minus X. Right? Oh, we already have H plus written down. And my HA, he's 0.52 minus X. Didn't really change much, but we'll write them down, all the digits. We could just as well have left it alone, right? We could have got by with leaving it alone, but that's okay. All right, so we put everything in. Put in all your concentrations. And that would pretty much be squared up on top, right? It's the same thing twice. All over. Well, I'm going to put in the exact answer. I don't think it's going to matter. I bet you'll get the exact same answer whether you use 0.52 or 0.518. Did you get an answer? 4 point what?
4.84
Times 10 to the negative? Okay. Yeah, if you get somewhere around 4.8 times 10 to the negative 6. The 10 to the negative 6 part everybody should be getting. The 4.8 might be jumping around a little bit, but I don't think so. Should be pretty close. There it is. Okay. Try this one. Find the concentrations of HF, H plus, and F minus in a 0.15 molar solution of HF. And I looked up the Ka for you. But not asking for pH. They just want to know what the concentrations are of everything at equilibrium. I see a lot of 0.01s for the concentration of H plus. So I think that's got to be right. If you're not getting it, check with your neighbor there. Make sure.
and then you gotta do the quadratic part.
Well, no, because it's 10 to the negative 4.
Oh.
So you don't have to. You can drop.
Just
You
right
say
there.
let's call that 0.15.
So just stop right there.
Yeah. All right, it's 10 to the negative 4, so you don't have to do that full quadratic. If you got it, go on to just see if you can wrap up EX5. Get them all done. You know what the squiggly lines means? About or approximately. Did you know that this is another way of writing that? With a dot on it? That's another way. The book, I'm not sure which way the book does it. But both of them mean approximate. They've done something, like what we're doing when they do this approximate kind of thing. Oh, 0.01. Well, let's see if you can knock out EX5 and then we can call it a day. Do you might get an answer for 5? 1.93? 1.9? Wow. Good. Yeah, if you got 1.93, have a good day. Mm-hmm.
I was looking over that, you know how they give you those books, like, for according to your degree plan, like what you should take? And for the chemistry one, it doesn't say analytical chemistry, but I thought you said we should take that one next. Didn't you say that one's like Chem 3?
I would.
Is that what you're, well, I mean, you're my advisor, so.
I would take organic next semester and analytical.
And then analytical?
Both of them at the same time.
Oh, okay. They're not like, well, I mean, that's fine.
Yeah.
And do you teach both of those, or just you and?
No, I just do analytical.
You do analytical and Mugia does organic?
Organic. Yeah.
But we find out later, like when we have to meet with y'all, right, to do our schedules.
You can come by anytime.
Okay.
Have you got any emails from me?
The one about
Because you should be,
scholarship?
yeah, you should be looking into that.
I looked into one of them, but I'm gonna go back and do it. Remember I had talked to you about it, and they told me like if you're going into med school or
Oh,
pharmacy,
that's
you can
right.
also-
Okay, well, forget that one. Look at the other ones.
Okay.